This is a lesson video for 5.2 Day 1. 5.2 is going to have some things about mean value theorem that we will get to in the coming days. But today, the two topics are increasing and decreasing functions, which will be easy given the things we've been working on with extrema, and then antiderivatives, which will be a concept we can do derivatives in reverse with. So as we look through what we're going to be working on, we need to connect some ideas that we've had from 5.1. In 5.1, if we were looking exclusively at a graph, and we could use graph as our reasons for things, then we could say that at A, there was a local maximum. And if we were just allowed to look at the graph, we would say because on the graph, we can see that F is increasing before we get to A, and it's decreasing afterwards. So if we were allowed to use the graph as evidence, that would be a reason why we'd call that a local max. If we weren't allowed to use the graph as evidence, we might say something like, well, we knew f prime was a critical point because f prime at A is 0. That made it a candidate for local extrema. And if we did some work with the function and its derivative, we could say something like f prime switches from positive to negative at x equals a. So depending on what we were allowed to use, if we were doing it strictly from a graph versus if we had to do it from the function or from information that wasn't graphically based. How could we explain that there is no extreme value at B? We could start by saying that we do recognize it is a critical point, and that might be why somebody thinks it could be an extreme value, but it can't be because, a little shorthand here, while f prime is 0 there, f prime is negative before and after. It's negative on both sides of x equals b. And therefore, we're decreasing. The function f is decreasing to get to b, and it's decreasing afterwards. So it doesn't change signs at b. We want to explain why we have a local minimum at x equals c, again, without using the graph as our evidence. We could say something like, we know that f prime at c is 0. That makes it a critical point. And then why is that critical point our relative or local minimum? Because f prime changes signs, changes from negative to positive at x equals c. And if we can identify what's going on with the derivative to make those maximum or minimum, the next idea that we're going to work on will actually go right along with that. So a corollary means it relates to something you've already established. So this corollary discusses what we know about increasing and decreasing functions. And what we know is that if a function's derivative is positive, then the function is increasing on that interval. So, and this is what it tells us. If the derivative is greater than 0 on a certain interval, then the function is increasing on that interval. And notice they say it's increasing on that closed interval. It's just its definition, how they write it. If f prime's positive over an interval, f is increasing over that interval. If f prime is less than 0, or what you might say is if f prime's negative over a specific interval, then f, the function itself, is decreasing over that interval. So how they're going to put that into action is they're going to ask us to find where functions are increasing or decreasing, and again, not using graphic techniques, but using analytical ones, things we can defend and back up without saying we saw it on a graph. So they want us to find the local extrema, good practice for us, and they want us to find the intervals where it's increasing and decreasing, which will just be a small add-on to the situation. So in examining my f of x function here, I see that my f of x function has a domain that's unrestricted. There is nothing that will cause the denominator to be 0. That denominator, in fact, x squared plus 4, will always be positive. And then that numerator could be all sorts of things, but that would not cause the function to not exist. So our domain is all real numbers. We have an unrestricted domain. Therefore, when we go to check the endpoints for local extrema, we don't have any. So that shortens our candidate list. We don't have any candidates that come from the endpoints. Then when we go to look for critical points to get additional candidates or places where the function could have a maximum or a minimum, we need to look at the derivative, and I supplied the derivative, not that we couldn't find it in the interest of time and big ideas, supplied the derivative, and so we need to look for where f prime would be worth 0. That would occur when that fraction's numerator is 0. And so in solving that, that would occur when x is plus or minus 2. Then we try to see where the function's derivative does not exist. And because the function's derivative is in fraction form, it's when that squared denominator would be worth 0. And here's what we know is that since this denominator is always going to be positive and I square it, there will be no values coming out of this. There is no place that x squared plus 4 quantity squared is worth 0. So as I go to look at my critical points and I go to think about what I know about whether or not they're going to be a max or a min or maybe just an inflection point, meaning not a maximum or minimum, those critical points sometimes are, I want to look at two things. I want to look at what the derivative's doing in between and what that tells me about the function. And if I do this, it's going to make answering the second part, the intervals where the function's increasing and decreasing, rather easy for us. So as I go to figure this out, I would look back up at my derivative and realize we've already decided that the bottom is always positive. The denominator is always positive. Therefore, as I'm looking at values in between -2 and +2 to choose to test that interval for my derivative, and I pick something simple like 0, when x is 0, and again, I would not record this as work. You'd be checking this either in your head or on the side. When x is 0, the numerator here is definitely going to be negative. The denominator is going to be positive, so our derivative when x is 0 is negative. What that tells me about the function f is that the function itself is decreasing on that interval. The slopes are negative for f, and therefore f is heading downhill or decreasing. Then I need to go check some other places, some other intervals. So I need to check something that's smaller than -2. So I might pick something like -3. I know the denominator is definitely going to be positive even if I put -3 into it. The numerator is going to be +9 minus 4. That's positive as well, so the derivative is positive for values less than -2. That tells me the function f itself is increasing on that interval. When I go to check one last value so that I've got all my intervals accounted for, I might check a nice easy positive number like 5 that will fall in that last interval to the right. Denominator is always positive here in this instance. Numerator is 25 minus 4, that's positive. Please do not assume that these will switch back and forth from positive to negative intervals. If we have one of those inflection points in here, we could have a negative interval or a positive. So as soon as I know that the derivative is positive in that last interval, I know that the function increases here. So in answering the two things they're interested in, they want the local extrema. So I don't need to worry about who my absolute maxes and mins are. I need to worry about local extrema only. My only candidates are -2 and +2. But I see that at -2, my function goes from increasing to decreasing. So that makes my value at -2 a local maximum. And I see that my function's value at -2 must be a local minimum because the function is decreasing to get to it and increasing afterwards. Using that information that I just stated then, I should be able to give intervals when the function's increasing and decreasing pretty easily. So I'd start from the left and say from -infinity up to my first point where the function's derivative changes sign up until -2. I know that that's a region where we're increasing. I also know that there's one more increasing region here from 2 until infinity. The way that the derivative, or the way that the increasing and decreasing regions are written, your endpoints actually count in there. If you check the definition in the book or on the previous slide, you'd see that they actually include the endpoints there. And it's just part of the definition of how they write increasing regions. So I'm going to go back for a second so you can see when they write then f increases on a closed region, decreases on a closed region. So my function's increasing on those regions, and then my region where it's decreasing is -2 to +2. So using what we already know, we'll get some good additional practice on finding extrema, and then we'll take advantage of that first derivative sign chart that we made that tells us things about f. Please make sure you label your charts like that. then you have to interpret what your chart tells somewhere in answers. Your chart itself will never be considered your answers or your justifications. The other topic that's in 5.2 is antidifferentiation. And antidifferentiation is a way of working backwards. If we're given f prime, it's interested in finding a function or a set of functions that could have been the original f function. So in other words, if we have a velocity, they're looking for us to find the position function, or if we have an acceleration, they're looking for us to be able to find velocity, to work backwards, so hence the name antiderivative. The problem is there are certain functions we're not going to be able to know exactly what they were before someone took their derivative. So I'm taking a look at the one in the middle here where they tell me that f prime is cosine of x. Well, immediately people always say, oh, then f of x had to have just been sine of x. And that might have been the function, but it's also possible that that function had a little bit more to it. It's possible that f of x was really sine of x plus 7. And in taking the derivative of the 7 term would have been 0, and we never would have known. So when we don't have more information, we always want to add a generic constant and make a general antiderivative, because we don't actually know a specific one. We don't know what the f of x function looked like exactly. We know it had to have had sine of x in it, but it's possible it could have had any constant added on the end, and that f of x would have then led to that derivative. So this is that general antiderivative, so that I'm reporting all the different functions that it could have been. So I'm going to go back to the first one then. So on the first one, they report that f prime was x cubed. We have to work backwards and figure out what the f function was. Well, if we know the derivative has an x cubed, we know the original had an x to the fourth because we take it down a power by that rule. But what I don't see in front of it here that's not there is a 4. There is no 4 in this derivative. So they didn't simply just take the derivative of x to the fourth. There must have been a coefficient here that allowed that 4 to get multiplied and turn into a 1 in the derivative, because there is no coefficient other than 1 here. So I need to think about when this 4 came down out front and got multiplied, what did it multiply by to make that 1? And in this case, it would be its reciprocal. So the beginning of the derivative must have been 1/4 x to the fourth, or function, not derivative, so that its derivative would be x cubed. But then again, we're going to add that constant on, because I don't know if it was 1/4 x to the fourth plus 7, 1/4 x to the fourth minus 2 pi. Could have been a lot of different constants added on there. So unless I had more information, I want to report all the antiderivatives that are possible for that function. The third example, they give us an acceleration function. They tell us the acceleration is 3. We know that acceleration is velocity's derivative. So this is really a derivative. If we'd like to work backwards and get velocity, then we need to take an antiderivative. So the antiderivative here would have been 3t plus a constant that could have been added on and would have come out as 0 in the derivative. So if we're looking for generic or general antiderivatives, we want to add that constant every time to account for all the different functions that could have had that derivative. Here's a case, though, where we can come up with a specific function and not have to have that plus c sitting there. So as I look at this one, they give me a derivative. F prime is 4x cubed. And I'm thinking, all right, my generic or general function that could have come from would have just been x to the fourth plus a constant. And check it, take its derivative, and see that you get 4x to the third. This would be the general, though, antiderivative. But they gave me more information. They told me a point f of x has to contain, and therefore I have a more specific set of information. I can come up with a more specific value to put here than that c. So if I happen to know that the function's value is 19, when x is 2, I can figure out what that constant should be. So 2 to the fourth being 16, that constant has to be a 3. So the most specific function, in other words, the exact antiderivative, not a general one, a specific one, is that this function had been x to the fourth plus 3, so that it contains that ordered pair, but also is the antiderivative to the situation. Using antiderivatives, then, we can figure out more complex problems. So as we were reading through FRQs, we were trying to figure out all the different cues that told us that we needed to do certain calculus operations. In this problem, it says on Earth, acceleration due to gravity is this. They gave me an acceleration function. So I'm going to record that my acceleration due to time is 9.8. If I read through the rest of the problem, a cell phone is dropped, tragedy. It takes 3 seconds to fall to the ground. They're curious what its speed was. Oh, speed is not acceleration. Speed is related to velocity, speed with direction. We happen to know that as it's falling, we know its direction, so our velocity will tell us the speed part. And how far did it fall? Well, how far did it fall sounds like a displacement or a location issue, so I'm pretty sure I'm going to need to know its position function as well. So starting from the acceleration function, that's velocity's derivative. So I should be able to work backwards and get an antiderivative that should represent velocity. And it looks like it had to have come from 9.8t plus a constant. Check to make sure that when you take 9.8t plus a constant's derivative, you get to 9.8. So your brain sees that direction that we're switching. But they gave me more specific information, so this constant isn't going to stay just generic. They told me that it takes 3 seconds for this to fall. Well, then I know the velocity at time 0. If this just dropped, I know that the velocity was 0 at time 0. And therefore, my constant in this situation, because of that, is 0. So my actual velocity function, specific to this situation, is just 9.8t. So when they ask what is its speed at just as it hit the floor, well, it took 3 seconds to fall, so I'm interested in its velocity at a time of 3 seconds because that's just as it's hitting the floor. So my velocity as it's hitting the floor, and we know they're telling us as it hits the floor, so we already know it's falling. My velocity when you calculate is 29.4 meters per second. So that answers the question of what's its speed just as it hits the floor. Grammar issue. The next question, though, is how far did it fall? Well, how far did it fall is dependent on its position. I know its position at time 0, and then if I could tell its position at time 3, I'd know the difference between the two is how far it fell. So I need a position function, and so far I have velocity, which is position's derivative, is 9.8t. So if I could work backwards and get an antiderivative for 9.8t, I know it has to have come from a t squared. And then that 9.8 must have come from the 2 from the t squared multiplying by something. So 4.9 multiplied by 2 would get me that 9.8. And again, plus a constant. If I think about this, I could say that my position at time 0, or the distance it had fallen, was 0 meters. So it had fallen 0 meters at a time of 0. So I have a specific antiderivative I'm looking for. Again, in this case only, the constant happens to be 0. So the position function that I can use to find location will be 4.9t squared plus 0. I know what happened at time 0. At time 0, the position is 0. It had fallen 0 feet. If I can see where the position was 3 seconds later, then I can figure out how far it fell. So my position at 3, evaluating that function, be 4.9 times 3 squared. And 4.9 times that comes up 44.1. So I know my position is 44.1 meters different than it was at time 0. So how far did it fall? It fell 44.1 total meters. Again, pause the video and go back and rehear or retry any of these to try to figure out how you're thinking this through. So your assignment, 5-2 day 1, these are the problems, and if you want to stay on the video a little bit longer so that you can actually use these as the online book, that's fine.